All right, everyone, welcome to the last GoLab talk of the day. We have a speech today, a two-part thing. We have a video first for running Go on the smallest systems with TinyGo, and after that, we're actually going to have half of it be live. So not just the Q&A, but Ayke will be live to do the second part. So I'm going to bring him on just for a moment to introduce you all to him, and then we'll get started. So let's bring you live, Ayke. There you are. Hi. Welcome to GoLab.
Thank you.
Yeah, we're happy to have you here. So let me tell you all about Ayke here. He has always been very interested in electronics, but somewhere around the age of 12, he started getting into programming Python, which is a language he still really likes. He didn't do much with electronics until he got an introduction into embedded software development with an Arduino Uno and really liked combining programming with the electronics hobby and doing much more interesting stuff. This really started to get interesting for him when he discovered MicroPython, which allows running Python on microcontrollers. So about our talk today, it is now possible to run Go on microcontrollers such as the Arduino and use it on the web with WebAssembly, all using TinyGo. TinyGo is designed to compile the same Go code you're used to down to much smaller binaries and thus brings Go to places it couldn't go before. While you may not be very aware of it, embedded software is everywhere. It comes from very small chips and remote controls to advanced automotive navigation systems and everything in between. While these systems used to be mainly written in C and still often are, more and more people are realizing that this is an aging language with many pitfalls such as buffer overflows, especially now that more and more systems are connected to the internet and thus are much more easy to exploit. Therefore, newer and more modern secure languages like Rust, JavaScript, and Python are being used for these systems for ease of programming and increased reliability and safety. Unfortunately, Go was not often an option because of its large binary size. Enter TinyGo. This project aims to support the same language with the same standard library and ecosystem while keeping binary sizes low. It runs comfortably on chips with tens to hundreds of kilobytes of program memory and then a few tens of kilobytes of RAM. TinyGo is also a viable alternative to Go on the web, as it does support WebAssembly. Again, binary sizes are much smaller, sometimes 3% of the size compared to the main Go support. This is very important for the web, as load times must be kept low because not everyone has a fast internet connection and unlimited data. So this talk will give you an introduction to the TinyGo project for those who are new to it. It will also give a short history of the project, including previous attempts to port Go to microcontrollers and why they failed. Further, it will include some technical details of how the compiler works and why it can produce such small programs. And finally, Ayke will show what is possible today with a few demos. So stay tuned, everyone, for the live part after the video, and enjoy. Thank you.
Hello, I am Ayke and I'm working on TinyGo. You may have heard about TinyGo already. It's a new Go compiler that, like GCC Go and the main Go compiler, but it specializes in the binary sizes are much smaller and that it uses less memory. These properties allow it to be used in places where Go was impractical or impossible before, like such as small embedded systems and WebAssembly. Therefore, TinyGo is not meant to replace any of the existing Go compilers, but rather it is a complement to them. In this talk I am going to focus on embedded systems, not on WebAssembly. I'll start with some history, give some insight into how it works, the current status of the project and what's next for TinyGo. Here is an example. This is a very small program that simply turns an LED on and off. This is like the hello world of hardware. The program configures the pin as an output pin and then turns it on and off in a loop. As you can see, TinyGo adds a new package to the standard library, the machine package. It implements low-level but portable access to hardware. It already has some things declared as a constant. For example, here you can see the machine.led constant declared. Most development boards include one or multiple LEDs that TinyGo will expose in this way. The machine package will also provide access to other things which embedded programmers are familiar with. These are SPI and I2C for communication between chips on a board, I2S usually used for transferring sounds, and of course UART, which can be used to transfer log messages from a microcontroller to the host computer if they are connected together. First, let's get some definitions out of the way. What does embedded mean? I personally define it as anything that runs code but does not look like a computer. This is a very broad range of devices. A more specific category of embedded devices is microcontrollers. These are small programmable chips with a CPU, memory and a huge range of peripherals to interact with the real world. Programs usually run directly from flash instead of being loaded into RAM first. And while they may be relatively fast, they are extremely constrained on memory. Okay, some history on TinyGo. I started looking into Go on embedded systems back when I was still using MicroPython. MicroPython is an interesting project that allows you to run Python on embedded devices which would normally be unable to run an interpreter. But while controlling some RGB LED strips, I was running into speed limitations, which I already kind of expected with Python. I could write MicroPython modules in C, but that kind of defeated the purpose of using an easy scripting language. So I started looking into running Go on these chips. My first attempt was to use GCC Go. GCC is normally used to compile C-like languages, but it can in fact also compile Go in the form of GCC Go. I realized that I could enable the GCC Go compiler in the toolchain I was using for the ESP32, the chip I was using at the time. Surprisingly, this worked. I managed to get a LED to blink, but didn't go much beyond that. I had hit several limitations with GCC Go. So I did the naive thing and tried how far I'd get writing an actual Go compiler. Pretty far, it turns out. Over the last 2.5 years, the project has gone from a small proof of concept to a whole community around this compiler, with contributions from many different people. The project includes now not just a compiler, but also a repository of over 50 different device drivers and a Bluetooth package that has support for Linux, macOS and some embedded chips. And a very active Slack channel, which you are welcome to join if you want. But before I wrote my own compiler, I searched the internet for something similar. I found a few projects, but none really fit my needs. The first one I found was mGo. What mGo does is convert Go to C and compile that. Unfortunately, while it does keep the Go syntax, it uses a C memory model. So, for example, you can't return a pointer to a local variable, something that is allowed by the Go specification. This means the language compiled is not compatible with the wider Go ecosystem. Other than that, I found various projects that attempt to use Go as a kernel language, most notably Gopher OS, which was presented at GoLab UK 2017, but appears to be dead now. Since then, a new and interesting project has emerged, TinyGo, which was presented here at GoLab earlier this day and also allows running Go bare metal. However, it is in fact quite different from TinyGo. It is a modified version of the Go compiler instead of being a new compiler and runtime. This allows it to be more compatible with the rest of the Go ecosystem, but it also means that it limits itself to much more powerful systems on chips, like the Raspberry Pi, which has orders of magnitude more RAM than some of the chips that TinyGo supports. In short, it's a different compiler with different goals, although it looks superficially similar. So, how does TinyGo work? TinyGo is not a compiler written from scratch. It uses many existing packages. For example, it uses the same packages used by Go tools and IDEs. If you think about it, what an IDE does to give you autocomplete and inline errors is already half of a compiler. To be able to give you good suggestions, it needs to parse and typecheck its source code, and in fact this is what TinyGo uses for the first half of the compiler, the so-called front end. Of course, a compiler is much more than that, and that's where a project called LLVM comes in. What's LLVM, you may ask? Well, LLVM is a toolkit for compilers. If you know the Gorilla toolkit for web applications, it's like that but for compilers. It provides all the language-independent things a compiler needs to do, in particular language-independent optimizations and generating machine code. Many well-known compilers such as Clang and the Rust and Swift compilers are based on it. LLVM also provides extra tools such as a linker. All of these things are used in TinyGo and are one of the reasons it can produce these small binaries for so many different platforms. Apart from just a compiler, TinyGo also replaces the runtime package. This is where a large part of the code size changes comes from, as we'll see next. So, how does TinyGo lower binary sizes so much? There are a few reasons to this, which I'll explain. In short, it's a smaller garbage collector, it's whole program optimization, and it's a different way of doing package initializers. Okay, first the garbage collector. In Go, there is no explicit way of freeing memory. And while the specification is silent on this, in practice implementations will use a garbage collector. Most tracing garbage collectors work in two phases. The first phase marks all reachable objects as reachable. It looks at all global variables and the whole call stack of each coroutine, so each function that is currently running and all functions that will eventually be returned to. And then it continues marking all these variables recursively. So for example, for each pointer, slice, map or channel, it looks at the values they point to. The second phase goes through all the objects on the heap and frees all objects that were not marked in the previous phase. As you can imagine, this is quite expensive. If you'd have a naive implementation, you'd need to stop all coroutines, do the scan, free all objects that are unreachable, and then resume all coroutines again. This is called a stop the world, as the program is stopped entirely. The Go runtime is smarter than this. It does almost all of this in parallel and only very briefly stops each coroutine to scan its tag, but otherwise the program continues running. For TinyGo, this is much too complex. It costs a lot of code size to do this. It also doesn't need all this complexity. TinyGo uses a very simple implementation in which it simply continues allocating from the heap until it runs out of space. And then it runs the garbage collector. It can of course use all available memory as it is the only program that's running on a chip. No need to worry about swapping or an operating system that might kill the process when it runs out of memory. This garbage collector design of TinyGo is an almost copy of the garbage collector in MicroPython. The implementation is different, but I decided to copy the design because I was already familiar with it. Next up is whole program optimization. TinyGo compiles and optimizes a whole program at once. This means we can get all the benefits of link-term optimization and then some more. One optimization allowed by this are much more efficient interfaces. Interface methods in Go are normally implemented in a way that's almost identical to C++ virtual methods. TinyGo, however, implements them in a very different way. Imagine you have code like is shown on the slide here. TinyGo transforms the code to basically a type switch. This is only possible because it knows all the possible implementations of the stringer type, and just checks them all. This might seem like it increases code size, however it also allows many optimizations. For example, it becomes possible to perform escape analysis across interface method calls to reduce pressure on the garbage collector. It also allows inlining functions if there is only one caller. This means that if there is only one implementation of an interface, all interface method calls will be converted to direct calls, thus making interfaces way less expensive. Unfortunately, these kinds of whole program optimizations are very slow to compile, especially for larger programs. Therefore, I hope to get a more traditional LTO setup in place in the future, which should keep most of the benefits of whole program optimizations while increasing compilation speed. The last optimization I'm going to talk about are package initializers. Say you have a global map like you can see here. You might expect this to be set at compile time. After all the values are already known and the compiler could just dump a ready-made map in the binary. Unfortunately, this is not the case. This is how the compiler sees it. As you can see, the map is not initialized at compile time, but at runtime. There are technical reasons for this in the main Go tool chain, but for TinyGo this behavior is a big problem, as this initialization code cannot be optimized away, even if the map is never used. Therefore, TinyGo implements partial evaluation of package initializers. This means it tries to run all the initialization code at compile time, including map initializers. If it finds a function it cannot interpret at compile time, for example, if it uses some form of I/O, it runs the function at runtime. This is difficult to get right, and I'm aware of bugs in the current implementation, but it is maybe the biggest reason why TinyGo's binaries can be so much smaller. Therefore, it is worth the investment. Also, I am working on an improvement of this partial evaluation that should make it much more correct. There are more optimizations, but these are some of the main ones. So, how close are we to a usable Go compiler? That really depends on your use case. It is able to compile most Go code or modify it. However, the big caveat is most. Many programs won't be able to compile because a dependency of a dependency somewhere uses a standard library package that is not yet supported. Over time, more and more of the Go standard library will become supported, while we keep binary sizes small, so this issue should disappear over time. That said, it already works really well for many smaller programs, which I'll show at the end of this talk. There's one thing which I would like to announce here, which I haven't talked about much before. You might know that TinyGo now supports Ide Integration, but I'm working on making the Ide Integration much better. This is a Go program written for TinyGo. As you can see, it blinks an LED like before, this time in a coroutine. Further, it also controls an LED strip. The program here animates an LED strip by first picking a color using a noise function, here. Noise functions are often used in computer-generated graphics. You could consider this strip here to be a very small image of just 8 pixels in total, the 8 LEDs. After calculating the colors, it writes them to the LED strip and waits a few milliseconds before doing the next update. Let's flash it to the board and to see what it does. Okay, great, it works. However, flashing to a board can be inconvenient during development. Some boards are slow to program or require manual action to program. So wouldn't it be nice to see what would happen during development? That's where the preview feature comes in. You might have noticed this button here. It compiles and it runs, the same as on the actual hardware. This is in fact the same program you can see here on the left, but running in simulation. Okay, what happens if we change something? Let's change a parameter of the noise function. It compiles and it runs again. This time there's less difference between the LEDs, as if the animation has been stretched out. How does this magic work? In this case, there's no emulation. Visual Studio Code has not suddenly gained the ability to emulate this board. Instead, the same program is compiled but using the WebAssembly target of TinyGo. In WebAssembly, the machine package gets a different purpose. All calls to it are propagated and the TinyGo extension for Visual Studio Code intercepts them to show what the board would do. This is not a perfect simulation, of course. For example, it has the speed and resources of a much more powerful computer, so it will not avoid the need for testing on real hardware. But if it works for most quick edit compile test cycles, that can be a big productivity boost. The question I get perhaps most often is, why use Go on embedded? Why not use C or C++? C is what almost everybody uses in the industry, and sometimes C++. Of course, I don't have to convince you that Go is a nice language and it would be great to run in bare metal, but there are very good reasons to use something other than the status quo, which is C. One reason is security. More than 2/3 of all security vulnerabilities in C and C++ are memory safety issues like buffer overflows. Any modern language prevents this, including Go. Switching to another language thus has a huge impact on safety. This is becoming more and more important now with lots of devices getting connected to the internet in the Internet of Things. The second reason is ease of programming. Go is inherently more portable than C, for example because the Go language specification leaves less room for variation and because of the strong standard library, which is the same across all operating systems. If you have ever used a cross-compiling toolchain, you probably know how difficult it is to set them up correctly. Both the Make Go compiler and TinyGo avoid all this, for example by using static linking by default. One exception I should add here is the Arduino environment. While it was designed for beginners, it does manage to avoid most of these issues, and I think that's one of the reasons it became so popular. The next one is concurrency, and this is where Go really shines. While most embedded systems are single core, they are very much concurrent. There are many inputs, many outputs, and lots of things running concurrently. That's why most bigger projects use what's called a real-time operating system, or RTOS. This is more like a library than an OS actually. They provide lightweight tasks and logs and channels to communicate between them. RTOSs also provide memory management, a hardware abstraction layer, and sometimes a network stack. Of course, all of this is already provided by the Go runtime or standard library. This means that, unlike in C, where you have tens of different real-time operating systems, concurrent code is easily shared between projects and even between server and embedded systems. And the last reason why I think Go would be a good fit for embedded systems is testing. Testing is perhaps the best way to improve software reliability. This is especially important for embedded devices as they are often run for years without interruption. Unfortunately, testing these systems is hard. How do you fire up continuous integration for custom designed hardware that you only have a few parts of? It's also partly psychology. The harder it is to test software, the fewer tests you will write. So how do you fix this? Well, you separate out hardware-specific code into the device drivers, manually test them once, and reuse those device drivers across projects. This works because drivers usually don't require a lot of maintenance. Then you use mocks or stubs to test the rest on standard hardware like your laptop and continuous integration. Replacing drivers with mocks or stubs is easy in Go thanks to interfaces. The current status of TinyGo test is that it works, but not everywhere. TinyGo has replaced the testing package with a custom version that is more memory efficient, and it can run these tests both natively on a desktop computer and in an emulation, but not yet on actual hardware. I'm working on getting that last bit fixed, and it should be supported in the near future. That said, if you're testing application logic instead of device drivers, you should be fine using just plain Go test for running tests, and using TinyGo build or TinyGo Flash to build firmware images. After all, it's the same language. Okay, now we get to the fun part. I would like to give a demo of something I wrote. It's called a so-called poi. A poi is usually a small weight on a tether that you can spin around. Most people will probably know this from fire spinning, although fire spinning is actually a relatively recent development in poi spinning. What is an even more recent development is using LEDs in these things. What I've used in this poi is a Nordic Semiconductor Bluetooth enabled microcontroller, a BMI 160 accelerometer and gyroscope, which measures rotation speed, and 2 LED strips. For that I use the SK9822 chips, which are in fact better for this purpose than the original. Most of the code is in reusable dependencies. I've talked before about the Bluetooth package, which is part of the TinyGo project. The motion sensor and the LED strips are both controlled with drivers that are also part of the TinyGo project. I also used an external hashing library for randomness. This external library was not written for TinyGo, but worked as intended on the first try. Thank you for listening.
All right, welcome back everyone. We're going to have the live session now with Ayke for screen sharing. So let me bring him on. Hello, welcome back. All right, shall I leave you to it to share your screen?
I was thinking of maybe answering the questions first and then doing.
You want to do that first? Okay, sure. Let's go ahead and answer some questions that were in Q&A, and then we can go ahead and proceed. So our first question from Darshan is, does TinyGo have similar features on any other IDE?
Not right now. I'm just prototyping basically. This is most of the code is still most of it is still hard code, but I intend to make it modifiable. It does rely heavily on web technology like WebAssembly, so you can't just use it in Vim, for example, without many changes. I do intend, however, to make it available on play.tinygo.org. which is basically the TinyGo playground, just like the Go playground, but it's not there yet. So in short, I don't have plans right now, but if it's a web-based editor, it should be able to possible to make it happen.
All right. Thank you. Second question is, does the select keyword fully work?
It works, yes.
Yeah.
So yeah, basically that's it.
Okay.
It was quite late, but I think it worked for a year or something now.
Fantastic. All right. Well, maybe we'll have some more questions come in later. That's fine. We can still save some time for Q&A even afterwards. So I'll let you go. I'll give you the reins to do your screen sharing, and hope everyone enjoys.
Thank you.
Yeah.
Let's see whether I can enable screen sharing. There you go. So for the second part, I am going to describe how TinyGo goes from resetting from random chip gets reset, for example, on power up to the main function. So let's consider this blinking LED example as an example. It's probably I'm going to describe this from the perspective of adding a new chip for new chip support to TinyGo, but it's probably useful for anyone who wants to improve TinyGo support or is just interested in how things work. I'll try to keep things understandable, so if you have a quick question, you can maybe ask it in the chat, but otherwise please keep it to the end. So the first thing you need when you want to add support for a new chip in TinyGo is a, hope this works. There you go. It's an SVD file. A SVD file is a XML file, as you can see here. It describes all the registers in a chip. And it's a lot of XML. In fact, it's so much that GitHub isn't able to show it. In TinyGo, we convert this to Go code. Here you see it. This describes all the interrupts available in the system. Here's some compiler magic, which you can ignore. And here are all the peripherals. For example, here's the UART. There's I2C, SPI, etc. It also, oops, this wasn't intended. Oh, there you go. It also generates a assembly file which contains the reset vector. You can ignore most of this, but this file will become important later. This function, this reset handler. Okay. So let's say you want to add support for a microcontroller in TinyGo. Apart from the SVD file, you also need the datasheet. For example, this chip is already supported, but I'm using this one as an example because I really like this one. This is a NRF chip from Nordic Semiconductor. The main thing you need to start is the memory map. So let's see. There you go. So there are two important bits of the memory, which is the flash here and the data RAM. You need to configure these, in the linker scripts, which is here. As you can see, this address is the same as this address here, which is the base of the flash, which is where all the code and constant data is stored. And the RAM starts at this address, which is the same as this address here, this one. The linker script is basically which defines where in memory everything gets stored. but for the most part, you can just use this as an example. Okay, let's say you have all of this set up. I mentioned the reset handler before. This is a, let's see how much time, okay. This reset handler is defined here in the runtime package. This is specific for this family of devices. The linker sees it as reset handler, although it's named main here, but it doesn't really matter. There's a system in it which is specific to this family of microcontrollers. I believe it fixes some hardware bugs, but I'm not sure. You can ignore this. There's a pre-init function. I'm not sure why this is marked as an error, but it is defined here. So I mentioned before that there's flash and there's RAM. The RAM is of course initialized at startup. So globals that can usually be modified would have some random value at startup. So they need to be initialized. 0 values are initialized here, and non-zero values are initialized here. For Cortex-M chips, you can just call pre-init, and basically that's it. Okay. Then there's the run function, and that's where things start to get interesting. This run function is defined here, and it initializes the heap. Here it starts the main Go routine, and then it keeps running the scheduler until the program is done, which is usually never on a microcontroller. Okay, so the init heap, the main Go routine first calls a special function called init all. This is a function that is known by the TinyGo compiler, and you can see here that it's defined, declared but not defined. What TinyGo does is it fills it with a code like this, like runtime.init, machine.init, main.init, etc. You get the point. But all of these packages are not known by the runtime, so this is done by the compiler. Okay. And this is what this does is call functions like so let's say you have this needs to be run at some point, and that's what init all does. Okay, there's post init, but it's empty for this chip. It's basically used on AVR, but nowhere else, I believe. And there's call main, and this is also a special function known to the TinyGo compiler. And what it does is it calls this calls the actual main function, this one here. So yeah, that's how you get to main, in short. But that's not all, of course. Let's say you have printed on hello. Oops. So where does this output go? This is defined in the runtime for each chip via some calls. It finally ends in this function, the puthar, whatever it's pronounced. And it writes to the UART, the first UART on the chip. This UART needs to be configured, which happens here. It uses a default configuration, and there's also some other initialization, the low frequency clock and the real-time counter. This is important for timekeeping. So that's how output gets written. What's maybe more interesting is how sleep works. Time.sleep is not actually defined in the time package, but in the runtime package. Let's see. Oh no, it's defined here. Here, see, time.sleep is defined here. What it does is it converts the duration to sleep, which is in nanoseconds. It converts these to an internal unit, which is ticks, which is basically the precision of the internal clock, which differs by chip. This nanoseconds to ticks is defined here somewhere. Here you go. So what the sleep function does is it converts the time.ticks. It gets the current go routine. This is an internal package, and it adds the current go routine to a sleep list, which is a linked list of go routines. How much time do I have? Okay, I have some time. And then it pauses the task. This means that a task is basically a different name for go routine. And pause means that it switches back to the scheduler, which you can see here. So go routine is resumed, and once the go routine calls pause, this function returns again, and the scheduler is invoked again. So this is, of course, a very simple program. It just sleeps. So what happens in the sleep is that the current go routine gets pushed to the sleep list in the order of wake up. So the first go routine in the sleep list is the one that first needs to wake up. And then the scheduler takes a look at whether there are any runnable functions. And if there are not, it will simply sleep for the duration until the first go routine is needs to run again. This is especially important for if you have multiple go routines running at the same time that sleep for different amounts of time. It has to pick the first one and just sleep for that amount of time. Sleeping is chip specific. It's this is some initialization code for which I'll skip over. It's defined in this function. So the scheduler calls sleep ticks, which is the same unit, I believe. So here you can see it just sleeps for whatever time is left until the next go routine needs to wake up. This one calls RTC sleep, and which in turn basically sets up the timer, waits, and then puts the processor to sleep until the first timer is done, basically. And this special function allows the chip to go into a low power state. And I have, in theory, this chip can go as low as, I believe, 3 microamps, not milliamps, microamps. Okay, so that's the sleep. Okay, there's one thing which is not visible here, which is getting the current time. This is also defined in the runtime. Let's see here, time.now. It basically calls the ticks function, which is also defined here somewhere. There you go. The meaning of this, you don't need to understand this, but this is very chip specific because every chip has a different set of clocks and timers and everything. So that's the main thing I wanted to explain. Maybe I can go in more detail, but maybe if there are questions, I can answer them first. I guess. But it looks like there are none.
All right, if you want to go on, that's fine too. You have plenty of time.
Okay. Sure.
I would say maybe another 15 minutes, and then we can go to Q&A.
Really?
Yeah, that's fine.
Oh, okay, that's more time than I expected.
Okay, let's say maximum at 40. So 15 minutes from now.
Ah, I see. Yes. Okay, so
Go for it.
maybe I can explain some more about how this is where the prepared stuff ends and the improvisation starts. Okay, so this UART, this is basically a serial port. You can simply use it from a application, from a program, write the UART, for example, in the echo example. It configures it, writes to it, reads from it, etc. How it works is maybe interesting. Let's see. So here are some defaults. But what you can see here is that the UART Okay, so I mentioned before all the auto-generated code. This is, let's see, this one uses the UART 0. It's this function, this struct. And all of this means that we don't need to know any hardware addresses for the all the registers in the UART. So how most of these microcontrollers work is that they have memory mapped I/O, which means that simply writing to a specific memory address, which is basically a pointer, or reading from it, interacts directly with the hardware. I see some matching. Okay. But using all those exact addresses is very difficult to do. So I'm very happy there are these SVD files, which are also used by the Rust project, the Rust Embedded project. In fact, this is heavily inspired by how Rust does the same thing. And this is basically, so this struct here, it looks like a normal struct, but in fact it's not really. You can see it's at a specific place in memory, and this place in memory is not RAM. This communicates directly with the underlying hardware. So, for example, maybe writing a byte is easiest to explain. Skip. So, writing a byte, it first looks at. No, wait a minute. Okay, what this does is it writes to a specific memory address, just this one byte. That's what happens here. This is basically just setting a pointer, but it has to be done with something like the volatile keyword in C, which is the set function here on the register. You could, TinyGo has something similar, but implemented differently. They also have some abstraction to make it easier to work with memory mapped I/O. But in TinyGo, it works different than in TinyGo. So it writes to this specific address, and then it busy loops until the byte has been written. So it reads from another address and checks whether the byte has been written, and if not, it just continues waiting until it has been written out on the UART. Reading from the reading from the UART is a little bit more difficult. Let's see. Not here. I see. So this uses interrupts. Interrupts use a bit of compiler magic in TinyGo. So this is not actually a normal function. It has some constraints, like this has to be a constant number, and this, oops, there you go. This has to be in a particular format. So this sets up an interrupt. For those who don't know, interrupts basically, it's like an event, like you see in JavaScript or wherever. An interrupt stops the program, whatever it's doing. It runs a special function, in this case, this function, and then continues. And when it returns, it continues running the code that was running previously. How it works exactly differs by chip architecture. In ARM, you can easily have multiple levels of interrupts. So a higher priority interrupt can in turn interrupt a lower priority interrupt and do whatever it needs to do. In other architectures, it's sometimes a little bit more difficult to get this working. So this interrupt, let's see. This compiler magic is used so that if you don't use the UART, which is unlikely for the UART, but let's imagine you don't use the UART, this entire interrupt handler is optimized away, which would not normally happen in C, for example, because the compiler, the linker specifically, has no way of knowing that this code is not used because it's part of the link script. So let's say you do want an interrupt for when a byte comes in over the UART. This has to be configured. The UART itself is enabled here, but the interrupt needs to be enabled separately, which is here. So how does the chip know which function to run? I'll ignore the compiler magic here, but what TinyGo basically does is it defines a function called, well, this. And the linker then knows to insert a function pointer at this location in memory, which is at the very start of the memory for this particular chip. So yeah, that's a very short introduction of interrupts. I can maybe take a look at GPIO. Pins are usually a lot easier. You need to configure it somehow, and then you simply write a. Here you can also see some weird thing of embedded software. So the GPIO, which is defined in this type here. This chip has 32 GPIO pins, I believe, and this register has 32 bits, so every bit in the register represents one port. So if the bit is high, the pin is high, and if it's low, the pin is low. And here you can see that this is not actually memory. This is a specific peripheral. So instead of, so usually what you want is atomically making a pin high or low. So what is usually done is you could just read the current state, set this one bit high or low, and then write it back. But that's maybe too slow, or it may be may introduce race conditions. So what some hardware does is it has this set and clear registers, which when read contains the same contents as the out register, which is it's still just a number. But when you write to it, something different happens. So, for example, the out set register is defined to so basically it does an OR with the current state and then current bit sets, and then sets that as the new out register. So this is okay. Something is happening. Okay, never mind. So this out set is writes to it and clear. It basically by setting a bit in this register, the out register is cleared, which is kind of counterintuitive, but this is basically a performance optimization. This is how this low-level hardware works. So that's, in short, what goes on behind the scenes of TinyGo. So I was wondering if there are any questions, maybe?
Yeah, hey, welcome back.
Hi.
Nice. I'm glad you were able to go more in depth with that in case anyone wanted to see a little bit more. So I'm glad you had time for that. So yeah, if anyone had some questions that weren't answered before, now would be the perfect time to do it. While we are waiting for those questions to come in, I just want to say thank you, Ayke, for being here, for being in GoLab virtually.
Thank you.
Absolutely. Is there anything else you wanted to say about being part of GoLab or about what you talked about today while we wait for questions?
Well, it's nice having me. Thank you for inviting me. And it's my first full-length talk, so I'm very happy that it went relatively smoothly.
It did?
Better than expected.
That's always a good thing, especially when you have to deal with technology.
Yeah.
Fantastic.
For some reason, Firefox didn't work for me, so I switched to Chrome. Things like that. But yeah, thank you for having me.
Yeah, absolutely. We're still waiting.
Yeah, I hope.
Oh, go ahead.
I hope I didn't get too technical in the last bit. It's very detailed, but for new people new to the project, this may be useful to know how this kind of thing works.
Absolutely. Yeah. I'm sure people have appreciated the little small details in it and to see behind the scenes for sure. Well, if that's it, a lot of people said, nice work. Oh yeah. Andrea Favilli has a question for you. Hi, Ayke. Is this your very first time at GoLab?
It's not. I went to GoLab last year in fall somewhere. In Florence, which I really liked. I went there by train from the Netherlands. So yeah, it's my second time.
Awesome. What was your experience like last time as a participant?
Wow, it was really great. I really enjoyed my time there. It's a nice city. Yeah.
Fantastic. Yeah. Andrea says, I remember you at the Ron Evans workshop. It was cool. He says.
Let's see. Yeah, there was a workshop. Ron does a workshop basically everywhere he can. And it's usually we have a lot of hardware laying around, and you can just play around with it. And if you have questions, you can ask one of the people. And I'm there, and Ron is there, and some other contributors to TinyGo are there. So yeah.
Fantastic. Well, hopefully in the future editions we can do this live, maybe back in Florida.
Yeah.
We'll see. We'll see how it goes.
Yeah.
All right. Well, if that's it for the questions, yeah, people are saying thank you. We want to thank you so much for coming, and hopefully in the future we'll see you as well, either as a speaker or as a participant. We'll be happy to have you either way.
Yeah. Who knows?
Yeah. Time will tell. All right. Well, if that's it for now, I'll just say hope you have the great rest of your day, and hope to see you around in GoLab.
Yeah. Have a nice day.
Thanks. You too. Bye.
Bye.
Awesome. All right, you guys. Well, that was the last talk for today for GoLab. Tomorrow we have 3 different things going on. We have a 3-hour workshop for you called Integrating Your Go Service with the ELK Stack, followed by 2 talks, Face Detection in Go and WebAssembly, and Lesson Learned, Go is not JavaScript. So wherever you are in the world, hope you have a great rest of your day, and we'll see you tomorrow at GoLab. Take care. Thank you. Bye-bye.